Good evening, everybody. Frequency response. Frequency response. The frequency response of circuit is the variation in its behavior with changing signal frequency. Okay, actually, here we are going to find circuit behavior with respect to frequency. Okay, means here we find first we find transfer function. Okay, then after we plot two graphs. Okay, one is magnitude plot, magnitude plot. Okay, and the other one is phase plot, and the other one is phase plot, Okay, magnitude versus frequency. Okay, this is here phase angle versus frequency. I'll come back to this plot. Okay, so next one is transfer function. Okay, here x of omega is the input given to the system. This is the input which is given to the system. This is the system. Okay, this is also called as network function. This is called as network function. Okay, x of omega is the input given to the system. Okay, where y of omega is the output getting from the system. Okay, so the ratio of output to input is called transfer function. Okay, here all are in frequency domain, x of omega. Okay, this is not in time domain. Okay, x of t means that function will be in time domain. This is time domain. Okay, omega means this is the input function in frequency domain. This is in frequency domain. Frequency domain. Whereas x of t means is the function, input function in time domain. Right. So the ratio of output to input is called transfer function. Okay, see the transfer function is x of omega of a circuit is the frequency dependent ratio of a phasor output x of y of omega to phasor input x of omega. Okay, it is the ratio of output to input is called transfer function. This is called transfer function in frequency domain. Okay, now let us find transfer function as well as frequency response for this circuit. This is the given circuit. Okay, RC circuit. Okay, for RC circuit, we are going to find circuit behavior with respect to frequency. That is nothing but what? Frequency response. Means you are going to plot magnitude plot. You're going to have magnitude plot as well as phase plot. You're going to have two plots, magnitude plot and phase plot. Okay, magnitude plot means magnitude versus frequency. Phase plot means phase angle versus frequency. Okay, then I mean first you are going to find transfer function. Transfer function means what? It is the ratio of output to input. Okay, so here this is the input voltage. You are collecting voltage across capacitor. This is the output voltage, right? This is the circuit which is in time domain. This is time domain RC circuit. Let me convert this time domain RC circuit into frequency domain RC circuit. Okay, then R remains same. R is independent of frequency. Okay, no frequency terms are present in resistance, right? So R is independent of frequency. So R remains same. Coming to this Vs of t, let us write Vs of omega or Vs, simply Vs. See, in time domain, In frequency domain, I can write impedance. Impedance, what is the impedance of capacitance? Zc is equal to what? 1 by j, 1 by j omega c. 1 by j omega c is the impedance of the capacitor, right? Okay, so you are collecting voltage at capacitor. Means you simply V0. You can say this is the voltage in frequency domain. Simply you can write it as V0 or V0 of omega. So both are correct. V0 of omega. Okay. 1 by j omega c is the impedance of the capacitance, right? Okay. This is a circuit which is in frequency domain. Okay. As this is in time domain, this is in frequency domain. Okay. Now coming to transfer function, h of omega is equal to ratio of output to input, right? So V0 by Vs or V0 of omega by Vs of omega. Okay, what is this thing? Let I of omega is the current flowing through this. Okay, let I of omega is the current flowing through this. Okay, so what will be Vs? Vs is equal to what? You're going to get I of omega. Okay, current into impedance, right? So total impedance R plus 1 by j omega c. Right? Okay, now coming to V0. How can I write V0? V0 is equal to I of omega into 1 by j omega c, right? Okay, so the ratio of V0 to Vs will be what? The ratio of V0 to Vs is 1 by j omega c by what this is R plus 1 by j omega, right? Okay, then you can have like this. Okay, so the final transfer function would be 1 by okay numerator is multiplied by j omega c, denominator is multiplied by j omega c, then finally you're going to get this 1 by 1 plus j omega rc. Okay, this is the transfer function. Okay, this is in time, sorry, this is in frequency domain, right? Okay, so this transfer function is having, this can be represented like this, right? Magnitude versus phase angle. Sorry, magnitude at an angle, phase angle.
Start this USR class.
Okay, h of omega, which is in frequency domain. Okay, h of omega is equal to 1 by 1 plus j omega rc, right? Okay, which is equal to magnitude. What will be phasor form? Okay, magnitude and phase angle, right? Magnitude at an angle, phase phi. Okay, so this is what magnitude. This is what phase angle, right? Okay, so let us find magnitude. H is equal to what? Or mod of h of omega. Mod of h of omega is equal to what? 1 by under root of 1 plus omega by omega naught whole square. Okay. Phase angle phi is equal to minus tan inverse of omega by omega naught. Okay, here it is given omega naught. Omega naught is equal to 1 by rc. Okay, here we have taken omega naught is equal to 1 by rc. Okay, see, what is the magnitude of this? This h of omega is equal to what? Magnitude and phase angle, right? So what is the magnitude? 1 by under root of 1 plus omega square r square c square. This is the magnitude, right? Okay, coming to phase angle, phi is equal to tan inverse of, okay, tan inverse of omega rc, omega rc, sorry, tan inverse of sorry, minus tan inverse of omega RC by 1, imaginary part by real part. Okay, when it comes to numerator, you're going to get this minus. Okay, so minus tan inverse of omega RC by 1. If omega naught is equal to 1 by RC, if omega naught is equal to 1 by RC, 1 by RC, then you're going to get, this would be omega by omega naught. Okay, this would be omega by omega naught whole square. If omega naught is equal to 1 by RC square. Sorry, if omega naught is equal to 1 by RC. Okay, then you're going to get magnitude like this. You're going to get phase angle like this. Okay, here omega naught, when omega naught is equal to 1 by RC, okay, then you're going to get magnitude like this, phase angle like this. So we have magnitude and phase angle, right? Okay, so what is the magnitude here? 1 by under root 1 plus, it is there, right? Okay, omega by omega naught square. Okay, omega by omega naught square. Okay, this is what, this is magnitude. Okay, h is equal to 1 by under root of 1 plus omega by omega naught square. Whereas what is the phase angle? Phase angle phi is equal to minus tan inverse of omega by omega naught, omega by omega naught, right? Okay, so this is called this is magnitude plot. This is magnitude plot or amplitude response. Okay, amplitude response or magnitude plot. This is magnitude plot. Magnitude plot. This graph is called magnitude plot because you are plotting magnitude versus frequency omega. Okay, here this is called phase plot. Phase plot, because you are plotting the graph between phase angle versus frequency. Here you are plotting the graph between magnitude versus frequency, right? Okay, so for different values of omega by omega naught, you're going to draw the graph. Okay, omega by omega naught is equal to 0, means h is equal to 1. Omega by omega naught is equal to 1, means 0.71. H is equal to 0.71. Omega by omega naught is equal to 2, means you're going to have 0.45. Likewise, okay, omega by omega naught is equal to 0, means h is equal to 1. Okay, next 0.71. Okay, 0.45. Okay, when omega by omega naught is equal to 10, h is equal to 0.1. Likewise, here varying frequency from 0 to infinity. You are varying frequency from 0 to infinity. See, magnitude plot means you are plotting the graph between magnitude versus frequency by varying frequency from 0 to infinity. By varying frequency from 0 to infinity. By varying frequency from 0 to infinity. Okay, so if you vary frequency from 0 to infinity, you're going to get graph like this. Okay, so this graph, you can say it is magnitude plot. This is called magnitude plot. Okay. Now, similarly, by varying frequency from 0 to infinity, okay, you are plotting graph between phase angle versus frequency. Phase angle versus frequency. Here, what is the graph? It is a graph between magnitude versus frequency by varying frequency from 0 to infinity. By varying frequency from 0 to infinity. You can see here, when omega by omega naught is equal to 0, means phase angle is 0. Okay, see, phi is equal to minus tan inverse of omega by omega naught. Tan inverse of 0 is 0. Okay, when omega by omega naught is equal to 1, means minus tan inverse of 1 is equal to what? Minus 45 degrees. Okay, when omega by omega naught is equal to 2, okay, 2 here, okay, 2 means you're going to get minus 60 degrees, means minus tan inverse of 2 minus tan inverse of 3 is minus 72 degrees, minus tan inverse of 10 means you're going to get minus 84 degrees. Likewise, you vary frequency from 0 to infinity. You know to have phase plot. You know to have phase plot. When omega by omega naught is equal to infinity, okay, the phase angle is minus 90 degrees. Okay, so that you can plot the graph between phase angle versus frequency. Phase angle versus frequency. Then that plot is called phase plot. Phase plot. This plot is called phase plot. Okay, so plotting two graphs, magnitude plot and phase plot, is nothing but what? Frequency response. Frequency response. Okay, we're going to find circuit behavior with respect to frequency. Okay, frequency response. Next, yeah, in frequency domain, this is the transfer function, right? Okay, this is also called as network function. H of omega is also called as network function. Okay, yeah, okay, this is in frequency domain. In frequency domain, the transfer function is defined. It is defined as the ratio of y of omega to x of omega, right? Okay, so x of omega is the input given to the system, y of omega is the output from the system, getting from the system, h of omega is the network function, right? So h of omega is equal to y of omega by x of omega. In S domain, okay, the transfer function is defined like this. Okay, you're going to have in S domain, the network function can be written like this: h of s in S domain, h of s. Inside, you're going to have system components. Okay, this is system transfer function. Okay, so x of s is the input given to the system, y of s is the output getting from the system. Okay, right? Then transfer function is equal to, it is the ratio of Laplace of input. Suppose, okay, if x of t is input, y of t is output. Okay, now transfer function h of s is equal to, it is the ratio of Laplace transform of input, Laplace of input to the Laplace of output. Okay, Laplace of x of t by Laplace of y of t. It is the ratio of x of s to sorry, y of t. This is x of t. Okay, Laplace of output, Laplace of input. Okay, so which is equal to what? Which is equal to y of s by x of s. Okay, so the transfer function h of s is the ratio of the output response or Laplace of output to the input excitation, that is x of s. Okay, with zero initial conditions. Okay, it is the ratio of Laplace of output to the Laplace of input. Okay, Laplace of, it is the ratio of Laplace of output to the Laplace of input. Laplace of output is equal to what? Y of s. Laplace of y of t is y of s. Laplace of x of t is x of s. Okay, so x of s, h of s is equal to y of s by x of s. Okay, this is the transfer function. H of s is equal to y of s by x of s. Okay, transfer function is the ratio of Laplace of output to the Laplace of input with zero initial condition. Okay, we got right. We have right x of s. Sorry, h of s is equal to y of s by x of s. What is y of s? Y of s is the Laplace of output. What is x of s? X of s is the Laplace of input. Laplace of input, right? Okay, so here what is the transfer function? It is the ratio of Laplace of output to Laplace of input with zero initial condition. Okay, so h of s is equal to y of s by x of s. Okay, so here let h of s is the transfer function. Here h of s is transfer function. Okay, x of s is the input which is given to the system. Okay, y of s is the input output getting from the system. Okay, so simply h of s is equal to what? Y of s by x of s. Okay, if h of s is equal to y of s by x of s means what will be y of s? Y of s is equal to h of s into x of s. H of s into x of s, right? And take the inverse Laplace transform to get y of t. Okay, let us find output in time domain. Okay, so you do one thing. Let x of t is equal to del of t. Okay, if impulse input is given to the system, what will be the output? Okay, so x of t is equal to del of t. If the x of t is equal to del of t, what will be the output? Okay, so right, y of s is equal to h of s into x of s, right? X of s, right? Okay, here x of t is equal to what? X of t is equal to del of t. Somebody unmuted their microphone. Mute your microphone. Yeah, fine. X of t is impulse input. Del of t. It is del of t. Del of t. X of t is impulse input. Means what will be x of s? Laplace of impulse. Unit impulse is what? Okay, unit impulse function is what? 1. It is equal to 1. When x of s is equal to 1 means what will be output? Y of s is equal to h of s into 1. H of s into 1. Then you're going to get y of s is equal to h of s. Y of s is equal to h of s. Simply apply inverse Laplace transform to this by taking inverse Laplace transform. Then this becomes y of t. This becomes h of t. Y of t is equal to h of t. Y of t is equal to h of t. Okay, so h of t is equal to what? Okay, Laplace inverse of h of s. Okay, h of t is equal to h of s. H of t is equal to what? Laplace inverse of h of s. Okay, that's why the term h of s, h of t, the term h of t represents the unit impulse response. Unit impulse response, as the input given to the system is unit impulse function. As input given to the system is unit impulse function. Okay, this term is called unit impulse response. Unit impulse response, because y of t is equal to h of t. Y of t is equal to h of t, right? Okay, so the term h of t represents the unit impulse response. Okay, it is the time domain response of the network to the impulse, unit impulse. Okay, this is the reason. Because of this, okay, h of t is called as unit impulse response. H of t is called as unit impulse response. Okay, simply if you are asked to find unit impulse response, simply h of t is equal to Laplace inverse of h of s. Means unit impulse response is equal to Laplace inverse of transfer function. Okay, if you are asked to find unit impulse response, then it is nothing but Laplace inverse of transfer function. Okay, so h of s is the Laplace transform of unit impulse function, unit impulse response of the network. Okay, so if you are asked to find unit impulse response, that is nothing but what? Laplace inverse of transfer function. Okay, now coming to poles and zeros. poles and zeros of a transfer function. Poles and zeros of a transfer function. Okay. So here already you know, right? This is the input given to the system. This is the output getting from the system. This is the network function. Okay, transfer function h of omega is equal to y of omega by x of omega in frequency domain. Whereas in case of S domain, h of s is equal to what? H of s is equal to y of s by x of s. Y of s by x of s. Right here, see, r of s is the input. See, you can also write x of s. Okay, here this is y of s. Here this is what? This is h of s. H of s. H of s, right? Okay. So here r of s is the input, g of s is the output. Okay, g of s is the transfer function. G of s is the transfer function. Okay, right? Here, see, what is c of s? C of s or h of s is equal to simply x of s into h of s. X of s into g of s or h of s. Okay, then c of s would be 1 by s into 1 by s into s plus 2, s plus 2 by s plus 5. This is the output. This is the output in S domain. Okay, by applying inverse Laplace transform, you can find c of t output in time domain using partial fractions. Okay, using partial fraction, you can find output in time domain by applying inverse Laplace transform to this c of s. Okay, so here transfer function is what? Here g of s is what? G of s or h of s. G of s is equal to what? Or h of s is equal to s plus 2 by s plus 5, right? Okay, so poles and zeros of a transfer function. This is the transfer function, right? This is the transfer function. T of s, you can also write it as t of s or h of s or g of s. Okay, so the poles of a transfer function are the values of the Laplace transform variable that cause the transfer function to become infinite. Okay, make it is equal to infinite. If you make this as equal to, if you make this equal to infinite means s plus 5 should be 0 or not. S plus 5 should be 0. Then s is equal to minus 5. S is equal to minus 5. This is what? This is called pole. Pole of a transfer function. S is equal to minus 5 is the pole. It is the pole of the transfer function. Pole of a transfer function. Okay, see here. The poles of a transfer function are the values of Laplace transform variable s. Values of Laplace transform variable s that cause the transfer function to become infinite. Okay, make it is equal to infinite means you are making denominator 0. Okay, denominator should be equal to 0. Okay, so if you make denominator is equal to 0, s plus 5 is equal to 0 means s is equal to minus 5. Okay, that is the pole. Okay, s is equal to minus 5 is the pole of a transfer function. It is the pole of a transfer function. Okay, it is what? It is pole of a transfer function. Okay, now coming to 0. 0, the sorry, this is zeros. Okay, zeros of a transfer function. Okay, the zeros of a transfer function are the values of the Laplace transform variable s that cause the transfer function to become 0. Okay, if we make this transfer function is equal to 0, making this equal to 0 means making s plus 2 0 or not. Okay, so s plus 2 is equal to 0. Making transfer function is equal to 0 means making s plus 2 0. Then s is equal to what? S is equal to minus 2. S is equal to minus 2, right? Okay, so this is called 0 of a transfer function. 0 of a transfer function. Okay, by definition, the zeros of a transfer function are the values of the Laplace transform variable s that cause the transfer function to become 0. Okay, making transfer function 0, nothing but s plus 2 is equal to 0, making numerator 0, making numerator 0, numerator of the transfer function 0. Okay, what is the numerator of the transfer function? S plus 2 is the numerator of the transfer function. You make that as 0. If you make that as 0 means s plus 2 is equal to 0, s is equal to minus 2, then that will be the 0. Value of zeros are the values of the Laplace transform variable. Okay, so value of s. Okay, what is the value of s? S is equal to minus 2. That is 0. That is called 0. Okay. Coming to poles, poles of a transfer function is the poles of a transfer function are the values of the Laplace transform variable s that cause the transfer function to become infinite. Means make transfer function infinite. Okay, making equal to infinite means making denominator equal to 0. What is the denominator of the transfer function? S plus 5. Okay, denominator of the transfer function is s plus 5. S plus 5, right? Okay, so you make s plus 5 0, then you're going to get s is equal to minus 5. Okay, or simply take transfer function, make numerator is equal to 0, then you're going to get zeros. Okay, making this equal to 0, s plus 2 is equal to 0 means s is equal to minus 2, then you get zeros. Making denominator is equal to 0 means you're going to get poles. You're going to get poles. Okay, so s plus 2 is equal to 0, then s is equal to minus 2, which is 0. It's called 0. 0 of a transfer function. S plus 5 is equal to, make denominator is equal to 0. Equal to 0, then s is equal to what? S is equal to minus 5. This is what? This will be pole of a transfer function. Making numerator equal to 0, we will get 0. 0 of a transfer function. Zeros of a transfer function. Okay. Making denominator equal to 0, you are going to get pole. If you have transfer function like this, s plus 5, okay, s plus 3, okay, s plus 2. How many zeros do we have in this transfer function? Okay, we have 2 zeros. Okay, zeros are s is equal to minus 3 comma minus 5. These two are zeros of a transfer function. Poles are s is equal to minus 2. Only one pole. Okay. See, in explain. Okay. Explain means is real part, imaginary part. Okay. Sigma j omega. Okay. Here s is equal to what? S is equal to sigma plus j omega, right? Here s is equal to minus 2. Minus 2. S is equal to minus 5. Okay. This is what? This is 0. This is what? This is pole. This is pole. Okay. 0 is indicated by the circle like this. Okay. Pole is indicated by cross mark like this. Okay. So this is what? This is 0. This is pole. Okay. Now calculate the gain. I naught of omega by I of omega, and its poles and zeros. Okay. Gain means what? Ratio of output to input. Okay. It is current gain. Okay, output current to ratio of output current to input current. Okay, so by current division rule, what is I naught of? See, it is parallel circuit. You're going to find I naught of. See, this is in time domain. Okay, let us draw the circuit in frequency domain. Okay, then I of omega resistance remains same. Inductance, here impedance. What is ZL? ZL is equal to J omega L. J omega L, right? So which is nothing but what? J 4 L. Where? Sorry. L is equal to 4, right? L is equal to 4, right? So which is nothing but what? J 4 omega. J 4 omega. Okay. And coming to this capacitance. Impedance of capacitance is what? Impedance of the capacitance is what? 1 by J omega C. Okay, C is 0.5 means you're going to get 2. 1 by 2 means 2 by J omega. 2 by J omega. Okay, this is a circuit in frequency domain. Frequency domain. Okay. So, I naught of omega, the current which is flowing through the capacitance, is what? Is equal to total current into opposite impedance. What is the opposite impedance? Impedance of this branch is what? Impedance of this branch 4 plus, sorry, L is equal to 2, right? So this will be J2 omega. Okay, so here by current division, output current I naught of omega is equal to total current, input current II of omega, right, into opposite impedance. What is the opposite? As you are going to find the current which is flowing through this, right? So what will be the opposite impedance? Opposite impedance will be this branch impedance. That is 4 plus J2 omega. This is the opposite impedance. Opposite impedance by total impedance. So 4 plus J2 omega plus impedance of the capacitor. Okay, 1 by J 0.5 omega. Okay, from this you are going to get like this. Okay, so here S is equal to J omega. Okay, put S is equal to J omega. Okay, J omega means S. Okay, 0.5 S into 4 plus 2S. Okay, you can have like this. 0.5 S into 4 plus 2S by 1 plus 2S, because S is equal to J omega. 2S plus S square. J omega square means S square. Okay, then you're going to get, this is the transfer function. Sorry, this is the gain. Okay, this is the gain. Okay, you can also say it as transfer function because it is the ratio of output to input, right? Okay, so the gain is S into, this is in S domain, this is in frequency domain, this is in frequency domain, whereas this is in S domain. Okay, roughly speaking, both are same. Okay, frequency domain or S domain, both are same. Okay, so in terms of S, this is the transfer function, right? Okay, so we got transfer function, right? We got gain. Okay, I naught of omega by II of omega, or I naught of S by II of S is equal to H into S plus 2 by S square plus 2S plus 1, right? So what are the zeros? Zeros of a transfer function? Making numerator is equal to 0. Making numerator equal to 0 means S into S plus 2 is equal to 0 means you're going to have zeros, 2 zeros. S is equal to 0, S is equal to minus 2. 0 comma minus 2. Coming to poles, making numerator equal to 0 gives zeros. Making denominator equal to 0 gives poles. Okay, so S square plus 2S plus 1, S square plus 2S plus 1 is equal to 0. Nothing more than S plus 1 whole square is equal to 0. Okay, you're going to have two repeated roots, two repeated poles. Okay, so double pole. Okay, S is equal to minus 1 comma minus 1. Two repeated roots, two repeated poles. Okay, the output of a linear system is y of t is equal to 10 e power minus t cos 4t u of t. When the input is x of t is equal to e power minus t u of t. Find the transfer function of a system and its impulse response. Okay. So transfer function. What is the transfer function? H of s is equal to what? H of s is equal to, it is the ratio of Laplace of output to Laplace of input. Okay. So y of s by x of s. Laplace of output to Laplace of input. Ratio of Laplace of output to Laplace of input, right? So y of s by x of s, right? So what is x of s? X of t is given. Okay. What is the Laplace of x of t? Laplace of e power minus t u of t, which is nothing but what? 1 by s plus 1. What is the Laplace of y of t? Laplace of 10 into e power minus t cos 4t u of t is nothing but 10 into s plus 1 by s plus 1 square plus 4 square. Okay. See, what is Laplace of cos omega t? Laplace of cos omega t is what? Which is equal to s by s square plus omega square, right? Okay, then frequency shifting property. Okay, Laplace of e power minus t cos of omega t, then which is equal to s plus 1. In place of s you write s plus 1, in place of s you write s plus 1. Okay, s plus 1 whole square plus omega square, where omega is equal to what? 4 here. Omega is 4. Okay, it is multiplied by 10. Okay, 10 into s plus 1 by s plus 1 whole square plus 4 square. Okay, here omega is equal to 4. Okay, finally we'll get transfer function y of s by x of s is equal to 10 into s square plus 2s plus 1 by s square plus 2s plus 17. Okay, this is the transfer function. Okay, now you are asked to find impulse response. What is the impulse response? H of t is equal to what? Laplace inverse of h of s. Laplace inverse of transfer function. Laplace inverse of transfer function. Okay, what is the Laplace of this transfer function? Okay, see, Laplace of transfer function, Laplace inverse of transfer function is, you apply Laplace inverse to this, then you are going to get Laplace inverse of h of s is h of t. Laplace inverse of 10 is nothing but 10 del of t, because Laplace of del of t is equal to 1. Okay, minus 40. Okay, Laplace inverse of this will be equal to 40 into e power minus t sin 40 u of t. You know, right? Okay, what is here? See, here we have frequency shifting operation. Okay, then s plus 1. S plus 1 means you're going to get e power minus t. Then after sin 40, sin 40 u of t, sin 40 u of t. Frequency shifting operation. Okay, finding transfer function h of s is equal to v naught of s by I naught of s of the circuit. Okay, already the circuit is given in S domain. Okay, this is circuit which is in S domain. Okay, by current division rule, I2 is equal to, okay, opposite impedance means s plus 4 by total impedance s plus 4 plus 2 plus 1 by 2s into I naught into total current. Total current is I naught, right? You know V naught. What is V naught? V naught is the voltage across 2 ohm resistor. Voltage across 2 ohm resistor is nothing but what? 2 into I2. Okay, already we got I2. Okay, then we'll get V naught. Okay, ratio of V naught of S to I naught of S, we'll get transformation. Convolution integral. Convolution integral. Okay, the convolution integral is used to, convolution means folding. Okay, okay. The convolution integral is used to find response y of t. It is used to find y of t. Okay, this is the formula. Okay, y of t is equal to integration from minus infinity to infinity x of lambda h of t minus lambda d lambda. Okay, so here uh, if if you have two signals, okay, then you're going to get output using convolution integral. Okay, convolution means folding, means if you have two signals, okay, let me have two signals like this. Okay, if we have two signals like this, okay, we can have convolution of both signals. You can have convolution of both signals, okay, by folding, multiplying point to point. Okay, you can have convolution of both signals, and finally you're going to get y of t. Okay, y of t is equal to, this is not into, okay, this is not multiplication of two signals. Okay, y of t is equal to x of t convolution by h of t. Sorry, y of t is equal to x of t convolution h of t, convolution h of t. Okay, we have one property. Okay, here we have to apply this formula in order to find y of t. Okay, you can use Laplace transform method. Okay, to find y of t. Here see, y of t is equal to x of t convolution. Y of t is equal to x of t, x of t convolution h of t, right? Convolution h of t, h of t. This is nothing but y of s is equal to x of s into h of s. Okay, finding convolution of these two signals, nothing but finding y of s and taking inverse Laplace of this y of s. Then you're going to get y of t. Okay, see, as desired, this indicates that convolution in the time domain is equivalent to multiplication in the s domain. Convolution in time domain is equivalent to multiplication in s domain. Okay, y of t is equal to x of t convolution h of t is nothing but y of s is equal to x of s into h of s. Okay, this indicates that convolution in the time domain is equivalent to the multiplication in the s domain. Okay, so for example, x of t is equal to 4 e power minus t and h of t is equal to 5 e power minus 2t. Okay, let me find convolution of here y of t. We are going to find y of t. Y of t is equal to h of t convolution x of t, right? So nothing but what, you know, right? Y of s is equal to x of s h of s, x of s h of s. Okay, so y of t is equal to, you know, h of t convolution x of t. This is nothing but, y of t is nothing but what, Laplace inverse of x of s h of s. This is nothing but Laplace inverse of h of s and x of s. Okay, h of s into h of s. Okay, so Laplace inverse of h of s into x of s, which is equal to Laplace inverse of, what is h of s? H of s is equal to, h of t is 5 e power minus 2t, means what is h of s? H of s is equal to 5 by s plus 2. X of t is 4 e power minus t, means what is x of s? 4 by s plus 1. Okay, then using partial fractions, we're going to get like this. Then applying inverse Laplace transform, you're going to get y of t. Let us take series parallel circuit. Okay. We do one thing. let us take series RLC circuit and let us find transfer function. Okay, so you take series RLC circuit. Okay. This is V I of S. That can drawing the circuit in S domain. R remains here. L. Okay. In S domain, what will be impedance? In frequency it is j omega, right? So this will be SL. S is equal to j omega. S is equal to j omega. In S domain, what is this? 1 by CS. 1 by CS, right? Okay. Let me collect voltage V naught of S across capacitance. Okay. So let us find transfer function. Here, what is transfer function? H of S is equal to what? H of S is equal to V naught of S by V I of S. V naught of S by V I of S. Right? So let us find I of S. Let I of S is the current flow into this. I of S is the current flow into this. Okay, then V I of S is equal to what? V I of S is equal to I of S into R plus SL, R plus SL plus 1 by CS. 1 by CS. What will be V naught of S? V naught of S is equal to I of S into 1 by CS. Current into impedance. Okay. Then V naught of S transfer function H of S is equal to what? What is this? This is V naught of S by V I of S. V I of S, which is equal to, we are going to get, okay, 1 by CS by R plus SL plus 1 by CS. Okay. Then V naught of S by V I of S is equal to, finally you're going to get like this. Okay. S square LC plus S RC, okay, plus 1. Okay, after simplifying this, numerator is multiplied with CS, denominator is multiplied by CS. Okay, then you're going to get this. So this is the transfer function of this series.